Welcome to Pure Mathematics 1, Chapter 3, Sequence and Series, topic Geometric Progression. And now we have to be careful with the term progression. The term progression has the same meaning with series, which means the sum of all terms in that sequence. It doesn't mean progression means sequence, so please remember that. So here, now begin with the definitions of a geometric sequence. The terms of a geometric sequence are formed by multiplying one term by a fixed number, the common ratio, to obtain the next. So I have a geometric sequence, is this one, 3, 9, 27, 81. For this one, the chain here is multiplied by 3, right? Chain in here is also multiplied by 3, multiply by 3, and multiply by 3. Keep going. Here's mean that this one is a fixed number. Fixed number, it doesn't change across the line. So we know that this one is a geometric sequence because first it can meet the demands of being a sequence because it is in a given order from small to high, and then it can meet the demands of being a geometric sequence because it has the next term is formed by multiplying one term by a fixed number to obtain the next one. So let's see whether this one is a geometric sequence or not. 125 by 1 0.2 ... Is it a geometric sequence? Yes, it is. Why? So this one, well, from 125, in order to get 25, we multiply by 1 over 5. And this one also multiply by 1 over 5, 1 over 5, and this one also 1 over 5. Multiply by 1 over 5. So this one is also a geometric sequence. So please remember that a geometric sequence is a sequence which can be formed when a number is formed by multiplying the term by a fixed number to obtain the next one. And now we look for some notation in geometric progression notation. For the first term, we often denote it as U1s, but for the notation in common, we use the word A because A is the beginning of the alphabet and the beginning of everything. So we choose A as a notation for the first term. For the common ratio equal to, the common ratio is denoted as R because R stands for ratio. No N here, ratio. And for numbers of term, it's called N because it stands for number here. And the last one, UK, indicate the position of a term in a geometric sequence. Like U1 mean that its position is 1. U5 mean that its position in a geometric sequence is 5. So now we'll look at this one, some magic in here. I have a sequence here: 1, 4, 16, 64, 256, and so on. I have A, which is the first term, equal to 1. I have U1, U2, here's U1 equal to A, U2 equal to A multiplied by 4 equal to 4, U3 equal to A multiplied by 4 square equal to 16, and U4 equal to A multiplied by 4 cube, to get 64. And the 4 here we can use the word R, because 4 equal to common ratio. The common ratio is R, so A multiplied by R. You can see that here for the part 1, when the position is 2, the powers of the common ratio is 1. So we have a general formula for a numbers in a sequence, geometric sequence, is that a u of k, the position k, equal to a multiply r to the powers of k minus 1. So what if we want to find the term u 100? We cannot keep multiplying by 4 up to 100. It's really hard. So we use this one in order to find that one. We know that a equal to 1 multiplied by, because r equal to 4, the common ratio here change 4, 4, 4, and 4 to the powers of k, it would be 99. So this one equal to 4 to the power of 99. In order to find the sum of a geometric sequence or geometric progression, you will use these formulas. But you might wonder why we have these formulas. Now I will do a proof to show you why we have this formula here. So have Fn equal to a ar plus ar squared plus up to a multiplied by r to the power n minus 1. And then we take r multiplied by fn. We'll have this one, ar plus ar squared plus ar cubed dot 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 up to ar n, because we multiply by r. So now we take this one minus this one here, so we have r minus 1 multiplied by Sn equal to, now this one minus this one will be a r to the power n minus a. So Sn will be equal to a multiplied by r to the power n minus 1 over r minus 1 equal to a multiplied by 1 minus r to the power n, or 1 over minus r. So on V2 you can both, because just changing the sign, we just change the sign one here and here. Just change the sign of the two in order to get the equation. Now we would look at the infinite geometric progressions. I have a geometric sequence which is this one, 1 over 2, 1 over 4, 1 over 8, 1 over 16, and so on. No end here. First we find a common ratio. Common ratio is 1 over 2. You see this one? Okay, so now we have the formula for the sum, Sn equal to a 1 minus r to the power n over 1 minus r. In this case, if we substitute r equal to what you want to find the values of this one, you substitute r equal to 1 over 2, so you will have something Sn. So you will take Sn equal to 1 multiplied by 1 minus 1 over 2 to the power n. Okay, 1 over 2 to the power n over 1 minus 1 over 2, which is equal to 2 multiplied by 1 minus 1 over 2 to the power n. you can see that if this one r, if n go to infinity, which is this one, because you have no n in here, so n go to infinity, 1 over 2 to the power n going smaller, and then 1 over 2, and this one will go smaller until it approach 0. 1 minus 1 over 2 to the power n will approach 1. So the sum Sn will approach 2. So the limit of this one is 2. So remember that it's only true for conversion progression. It's only happen for conversion progression where it's occur where here's minus 1, is r 1, or the absolute values of r smaller than 1. It's only occur when r ranging from minus 1 to 1. It will never occur in the case where the equation is divergent, which is here greater than 1. Mean r greater than 1 or r smaller than minus 1. It will never happen with this case, but it will happen with the case of conversion. It will approach a point. So for this type of thing, we remember that when n approach infinity, so r to the power n approach 0. So this one, 1 minus r over n, r to the power n approach 1. And if you substitute it into the equation, you will have something like this, because this one approach 1. So Sn equal to a over 1 minus r. So for any infinite geometric progression which has no n in here, as it go to infinity, and the common ratio, which is r, is ranging from this one, from minus 1 to 1. It can be any number like 1 over 3 or minus 1 over 6 or something like that. They can range in any value which is in this range. So we have a formula to the sum, which is this one, Sn equal to a over 1 minus r. Let's say for this case, r equal to 1 over 2. So we have Sn, the first term is 1 over 1 minus 1 over 2 equal to 2. So that approach to that. For another example, I will take is that here I have 0.2, and here 0.22, 0.02, and here 0.002, and to infinity. I want to find the sum of this one. So I know that the r equal to 0.1, right? So we have our first value is 0.2 over 1 minus 0.1. It's 2 over 9.